Very good morning. Today we are going to see about the unit commitment problem and what are the techniques in your unit commitment problem and how we are going to solve this unit commitment problem. So if you see, take like this unit commitment problem is one of the important optimization problem in the power system objective operation. One of the important optimization problem in the power system operation. The objective of the unit commitment is to schedule the generating units online or offline over the scheduling period or horizon such that the power production cost should be minimized with the total demand fully met and operation condition satisfies. Okay, so the definition of the unit commitment problem goes like here. That is, the unit commitment problem is an important optimization problem in the power system operation. The major objective of the unit commitment is to schedule the generating units online or offline over a period of time, that is scheduling horizon, such that the power production cost is minimized with the load demand fully met and the operation constraints satisfied. So that is called the unit commitment problem. This unit commitment is combinatorial in nature and also consists of many hard constraints. In solving this problem, the generation schedules are first found, then the costs are evaluated to the economic the load dispatch calculation. So it is defined as optimal allocation of the optimal allocation of number of units to be operated, that is to determine the units of plants that should be operated for given load. Given load is the problem of the unit commitment problem. The main purpose of unit commitment is to find the optimal subset among the best subsets which provide the minimum operating cost. So in economic load dispatch, what we are doing in economic load dispatch, we are trying to find out the the fuel cost, the minimum cost of the generation, cost of the fuel cost of unit total fuel cost of unit 1, unit 2 and unit 3, and also the dispatch generation, the amount of power is being dispatched from the first generating unit, second generating unit, third generating unit. That is, say for example, if we consider three generating units, we are going to find out power generation from the unit 1, power generation from the unit 2, and the power generation from the unit 3, that is PG1, PG2 and PG3. Okay, just we are finding out the fuel cost of that power generators, that is one whatever the generating units we have considered, and also at last cost. So here, when in unit commitment problem, we have to find out which is the least cost generator. Okay, and also that least cost generator, so that we can commit for that particular unit, so that the cost of the generation also, that is cost of the generation also will be reduced. Okay, so like 10 generating units of that, which generating units we need to commit. We need to commit means we need to select so that it should be in the operation. Okay, that generators should be in operation, and also the power protection cost will be minimized, and also with the satisfying the all the constraints. So whatever the constraints, minimum maximum constraints, all the with satisfying all the constraints, we have to commit the particular generating units. So that is the main objective of this unit commitment problem. So unit commitment solution methods. The commitment problem becomes very difficult as the theoretical exercise. Let us postulate the following situation. Why it is this unit commitment problem is very difficult. We establish the loading patterns for m period. Say we are considering the loading patterns for m periods. We are considering m periods. Okay, so one period maybe one day or to like a 30 days or 1 year like that. So say for example 30 days in a month, m periods we are taking. So we have n units to commit and dispatch. We have n generating units to commit and dispatch. Okay, the m load levels and n operating limits on n units are such that any one unit can supply the individual loads, and that any combination of units can also supply the loads. Okay, the M load levels and the operating limits on N units are such that any one unit can supply the individual loads, and that the combination of units can also supply the loads. Let us assume we are going to establish the commitment by, okay, commitment by this enumeration, that is number of the total number of combination that we need to try for each hour is C of n comma 1 plus C of n comma 2 plus up to C of n comma n minus 1 plus C of n comma n, that is equal to 2n power 2 power n minus 1, 2 power n minus 1. So these are the number of combinations we are going to try in a particular every hour. So that is of this combination C of n comma 1 plus C of n comma 2 plus up to C of n comma n minus 1 plus C of n comma n is equal to 2 power n minus 1, where n comma j, n comma j is the combination of n items taken j at a time, where n c of n comma j is the combination of n items taken j at a time. That is c of n comma j is equal to n factorial divided by n minus j factorial into j factorial. Okay, like permutations and combinations, you already studied this formula. Okay, the combination formula, that is C of n comma j is equal to n factorial divided by n minus j factorial into j factorial, where j factorial is equal to 1 into 2 into 3 up to into j. For total period of m intervals, the maximum number of possible combinations may be of 2 power n minus 1 the whole power m. 2 power n minus 1 the whole power m. For total period of m intervals, the maximum number of possible combination. So this is of the maximum possible combination, that is 2 power n minus 1 the whole power m. Okay, which becomes a horrid number to think about. So we'll see the example. For example, if you take 24 hours period, 24 intervals of time, that is 24 1 hour interval, and let us consider the units of size 5, 10, 20 and 40 generating units. Okay, so we are considering 5, 10, 20 and 40 generating units. The value of 2 power n minus 1 the whole power 24 becomes the following. Okay, so now we are going to find out, that is this is the number of generating units, this is the combinations. Okay, the maximum combination, that is 2 power n minus 1 the whole power 24 for 5 generating units. Let us take 5 generating units, so you have to substitute 5 here. So 2 power 5 minus 1 the whole power 24. If you take your scientific calculator, if you calculate like this, okay, so it will come like 6.2 into 10 to the power of 35. 6.2 into 10 to the power of 35. Next, again for 10 generating units. So it is not a very simple number. 6.1, the number of combination is 6.2 into 10 to the power of 35. Okay, so 10 to the power of 35 means it is very very used for 5 generating units itself. Say for example 10 generating units. You just take your scientific calculator and calculate now itself. So again, 2 to the power of 10 minus 1 the whole power 24. So if you calculate, it will come like 1.73 into 10 to the power of 72. I think in your scientific calculator, FX calculator, you can easily do this calculation. Next, EX also you can do, but FX is very, very easy. Next, 20. For 20 generating units, 3.12, like if you substitute 3.12 into 10 to the power of 144, 10 to the power of 144. So I think 144 zeros. 3.12 into 144 zeros you have to add here, 1.73 into 72 zeros you have to add here, also 35 zeros you have to add. So for 40 generating units, okay, so if you calculate in your calculator, if you calculate, go take your calculator and you calculate like 2 to the power of 40 minus 1 the whole power 24, it will come like math error. Math error. Why in your scientific calculator it is coming like math error? Because this number is very, very big. Even your scientific calculator also will not able to calculate. Okay, so in MATLAB sometimes you can get this answer, depends on the versions. MATLAB you can get. Okay, sometimes in MATLAB also it will come like error, not a number, or like that it will come. Okay, so this much complexity the combinations are. If you want to calculate this combination, so it is very, very complex. For 5 generating units itself it is very complex. For 20 is also well. 40 is very, very complex. There are very large numbers are the upper bounds for the number of enumerations required. Fortunately, the constraints on units and the load capacity relationship of typical utility system are such that we do not approach these large numbers. Okay, so we do not approach these large numbers. Nevertheless, the real practice barrier in the optimized unit commitment problem is high dimensionality of the possible solution space. Okay, so in the real system, if you take the whole state, how many generating units will be there? Like a minimum, like 100 generating units will be there. Like more generating units will be there. So if you go for doing the unit commitment for whole state, so that whole state, that will be the very, very complex thing. Complex, very, very complex. You can't able to solve. Okay, so like that, what they will do is area wise they can do, area wise, district wise, how many generators, 10 generators or 20 generators, like that they can program. Okay, even like hand calculation, you can't able to solve this many combinations. Okay, hand calculation, it is very, very um, difficult. So they will go for a computer software, they will go for developing a computer software, like programming in MATLAB or some other softwares, so that it may easily done this job and it may give the solution combination. This many combinations it has to be done. So 10 to the power of 144, 144 zeros, 3.12 into 144 zeros combinations, it has to be done. So I think it will take 10 minutes, 15 minutes of time to calculate that combination itself. Why? Because that many combinations that particular program has to give. So 10, 20 minutes, half an hour, 1 hour also it may takes. Depends on the size. And also sometimes math error also will come. Why? Because your calculator also, your super calculator, like MATLAB also sometimes will be not giving the answer. So that's why we are going for, if 40 generating units is there, then in that scenario what they will do is they will go for 10 10 10 10 into 4, like that they may go for combinations. Okay, that also very, very difficult, but even though I'm telling, so 10 10 10, like that they may go for the combination. The most talked about the technique solutions are, what are the solution methodologies of this unique commitment problem are, first one is priority list method, then dynamic programming method, then Lagrange's relaxation method, right? Lagrange's relation method, priority list method, dynamic programming method, then Lagrange's relation method. Okay, coming to the priority list method, this is the simplest unit commitment solution method. Okay, this is the simplest method when compared to all other two methods. Dynamic programming method also very complex, but if you go for fuzzy logic programming, then it is somewhat easy. Not that much easy. It is somewhat easy. Okay, if your program is complete, okay, if you are going for programming for 40 generating units or 20 generating units, the entire program is completed, then after it is easy, but doing the program and relating the things is very difficult. So dynamic program and Lagrange's relationship method also, it's not majorly used, but it is also very simplest method. So we are going for priority list method. Priority list method. Okay. So what is meant priority list method? By using full load average protection cost. Full load average protection cost in the short form FLAPC. First letter FLAPC. Priority list method using full load average production cost FLAPC method. Okay, sometimes it is called as FLAPC method also. So priority list method. What is the priority list method? Priority list method is the simplest unit commitment solution method, which consists of creating a priority list of units. Okay, so what we are doing is we are framing the priority list. We are framing the priority list. The priority list can be obtained by noting down the full load average production cost. Full load average production cost, that is FLAPC of each unit. Okay, the priority list can be obtained by full load average production cost of each unit. So how to calculate this FLAPC, full load average production cost? That is nothing but net, okay, net heat rate, net rate at full load, net heat rate at full load into the fuel cost. Okay, so net heat rate at full load into the fuel cost. Okay, the fuel cost you can take like in rupees symbol, we have used for solving the problems. Like that also fuel cost you can take. In some other things, dollars also you can take. In foreign currencies you can go for dollars. Fuel cost in dollars. Some notation it is given like K, small k as fuel cost. Okay, small k also you can use. That is your own choice. Whichever is easy for you, you can go for that notation. Okay, rupee symbol or dollar symbol or the small k notation. That is FLAPC is nothing but, okay, net heat rate into fuel cost. Net heat rate at full load into fuel cost. So net heat rate we know, that is HI of PGI divided by PGI into K, that is fuel cost is nothing but K. So that's all. FLAPC is nothing but net heat rate characteristics at full load into fuel cost. That is the formula. So net heat rate is nothing but HI of PGI divided by PGI. What are the steps for solving the priority list method? So there are, we are going for certain assumptions. Why? Because this unit commitment problem, as I said, it is very complex to solve. Okay, the load may be changing minute by minute. Demand may be changing minute by minute, even in second also. Second by second, it might be changing. So no demand will be constant. If you take, you can predict the demand approximately, but no demand, whatever in the world. So demand, power demand is never constant. It might be changing, decreasing or increasing. There are average, increasing, decreasing, like that. It might be changing only, but it might not be constant. So that too, if you going for solving this unit commitment problem. So you know the complexity for 5 generating units, how much combination. We are going for calculating the committing that particular generating unit. Okay, so for 1 hour like that combinations are more. So what we are doing is we are considering certain assumptions and we are going to solve this priority list method. We are going for certain assumptions so that the complexity is somewhat reduced so that we can get to some like approximate in that particular minute or in the particular hour what might be the generation, what might be the committing, how we are going to commit, like that we are going to calculate. So in that there are following assumption. Assumption number one: no load cost is assumed to be zero. No load cost is taken as zero. Okay, no load cost is taken as zero. But in practical, even though cost load is there or not, load is not there. Okay, there will be some minimum tariff they are going to give. So, but here no load cost we are assuming that as zero. Next, unit input output characteristics are linear between zero and full load. Okay, unit input output characteristics are linear. So that characteristics we have seen, no, thermal power station. So that should be linear, like that they are saying. So unit input output characteristics are linear between zero and full load. Next, startup cost are of fixed amount. Startup cost are assumed to be fixed amount. Okay, startup cost, what we are considering is we are considering that as fixed amount. Next is ignore minimum uptime and minimum downtime constraints. Okay, in economic load dispatch we have considered, no, like a minimum uptime and minimum downtime. So that minimum uptime and minimum, so for operating there is some minimum uptime and downtime. Like it should not reduce for 2 hours, it should not exceed 8 hours. Like that, some constraints might be there for some thermal. If you take like thermal generating units, so minimum operating time you have to operate for 4 hours. So to the maximum of 6 hours or 8 hours, like that some uptime and downtime constraints are there that we are ignoring over here. Next, determine the full load average production cost for each units by using FLAPC. That we have seen, that is FLAPC is equal to HI of PGI divided by PGI into K. So this is the steps. First step for calculating the priority list method is first we have to determine the full load average production cost for each generating unit by using this formula. Okay, that is HI of PGI divided by PGI into K, that is cost. Okay, cost of that particular unit. Okay, next second step is first full load average production cost. Second step is form priority order based on form the priority order based on average production cost. Okay, from the priority order list based on average production. Step number 2. Step number 3 is commit the number of units corresponding to the priority order. Commit the number of generating units corresponding to the priority order. So even you have to commit the units corresponding to the priority order, you have to commit. So whichever the priority, like FLAPC is there. So while sorting, after sorting, similarly corresponding generating units you have to sort in the priority order. Calculate, next step, calculate PG1, PG2 up to PGN from economic load dispatch problem for the feasible combinations only. Okay, so what we have to do is we have to calculate PG1, PG2 up to PGN from the economic load dispatch problem for the feasible combinations only. So next step, for the load curve, assume each hour load is varying. For the load curve we have seen, no, in that load curve, assume like each hour load curve is varying, not at a constant. Okay, each hour the load is varying, like that we have to assume. Next, assume load is dropping or decreasing. Determine whether the dropping the next unit will supply generation and spinning reserve. Okay, assume load is dropping or decreasing. Determine whether the dropping the next unit will supply generation and the spinning reserve. If not, continue as it is. If yes, go to the next step. Okay, if not, continue as it is. If yes, go to the next step. Okay, so next, go to the next step. So next, determine the number of hours before the unit will be needed again. Okay, determine the number of hours h, capital H, before the unit will be needed again. Okay, that is the next step. So next step, check H is capital H is, that is number of hours H is less than minimum shutdown time. Check the capital H is less than minimum shutdown time. If yes, go to the last step. Okay, if not, go to the next step. Okay, if yes, go to the last step. Okay, so next, what we have to do is we have to calculate the two costs, sum of hourly production cost for next h hours will be with the unit up. Okay, next recalculate the same for the unit down startup cost for either cooling or banking. If the second case is less expensive, then the unit should be on. Okay, repeat this procedure until the priority list. Okay, this cooling and banking you just neglect. Okay, so direct away you just come here. Okay, if check here, H is less than minimum shutdown time. Okay, next, repeat the procedure until the priority list. Like that you can go for. While solving the problem you can clearly understand. While solving the problem you can clearly understand. So what is the first step? First step, we have to calculate, determine the full load average production cost for each generating unit, that is FLAPC. Next, we have to form the priority list based on the average production cost, that is in ascending order. Next, commit the number of unit corresponding to the priority order. So we have sorted priority like FLAPC in ascending order, no. Meanwhile, whichever the like FLAPC belongs to which generating unit, that generating unit we need to sort. Like FLAPC, say for example in the priority list, so first we are sorting like FLAPC 3, third generating unit, then FLAPC 1, then FLAPC 2 means corresponding generating units, that is minimum and maximum generating units you have to sort, like that. Like that they are telling. Next, calculate PG1, PG2 up to PGN for economic load dispatch for the feasible combination only. Okay. Next, for the load curve, each hour load is varying. Assume the load curve, each hour load is varying. So that assume the load is dropping or decreasing. Determine whether the dropping the next unit will supply generation or spinning reserve. If not, continue as it is. If yes, go to the next step and determine the number of hours H before the unit will needed it again. If H is less than minimum shutdown time, then go to the last step, that is repeat this procedure until the priority list.